Hello everyone. In today's video, we'll be talking about how to find the material derivative of a position vector. So let's take r as the position vector. So r equals xi cap plus y j cap plus z k cap. But the notation which I'll be using here is one of column vectors because I find it more convenient than writing I cap, j cap and k cap. So here we have r, right? Now let's consider the material derivative. So for a general property, this can be vector or scalar, a general property phi, we know that the material derivative d phi by dt, where d is capital, the material derivative of phi with respect to time is equal to del phi by del t plus v cross v dot the del operator into phi. So this is known for any variable in a flow field. So now if we take phi equals to r, that is if we take r as phi, then d phi dr by dt would be equal to del phi by del t plus v dot del operator phi r. This is r as well. Now let v, the velocity at a point xyz, be equal to u v w. These are the x, y and z components respectively of velocity. So the reason why I've taken this example is because the derivative of position vector with respect to time, the material derivative, should give us velocity. So this should be a very interesting result. So now let us substitute on the right hand side of this expression d r by dt equals del r by del t. So del by del t of x, y, z plus now v dotted with the gradient. So we know that the gradient operator is nabla is equal to del by del x, del by del y and del by del z, right? So if we take this information, v dot this gradient operator nabla would be equal to u del by del x plus v del by del y plus w del by del z of r, which is x, y, z, right? So now let's continue. So del x by del t, del y by del t and del z by del t. This is simply, I've taken del by del t over here inside the bracket, right? So this plus now u, so this whole term gets taken inside both inside all three of these coordinates x, y and z. So u del by del x times with taking x would give us simply u, and v del x by del y. Del x by del y would simply be 0 because x and y are independent of each other, and similarly w del x by del z would be 0. So in the first coordinate we have only u. Similarly in the second coordinate you have u del y by del x. Del y by del x is again 0. V del y by del y. Now del y by del y is simply 1, so we have v. And w del y by del z, del y by del z is 0, so we simply have v. And z. And in the z coordinate, in the third coordinate, we have w in a similar way, because del z by del x is 0 and del z by del y is 0. So here we have a very interesting result. U v w, this is nothing but y. So, and we also know that the left hand side would be equal to v, because velocity is defined as the rate of change of position vector, position. So v is the material derivative of r with respect to t. Now this gives us a very important result. So on the left hand side we already have v. On the right hand side we have this expression over here, del x by del t, del y by del t, del z by del t, and plus v. So why is this interesting? Because this gives us 0 equals del x by del t, del y by del t, del z by del t. This entire expression becomes the 0 vector. This is not a scalar 0, this is the 0 vector. So you can also write 0, 0, 0. So this to me was quite confusing at first, because I had expected del x by del t to be equal to u, because u is the component of velocity in the in the x direction. So I had expected del x by del t to be 0, to be u, but this is not the case. And similarly del y by del t is also not equal to v, and del z by del t is not equal to w in general. And why is this the case? Here comes the understanding of Lagrangian versus Eulerian method. So these x, y, z and this entire material derivative is meant for an Eulerian approach, where we do not consider individual particles, rather we consider the flow field. So here the x, y, z and t are all independent parameters. So in the same way as del x by del y is 0 and del y by del x is 0, for the same reason del x by del t, del y by del t and del z by del t are also 0. This is a very important understanding, because if instead of this you substitute u for del x by del t, v for del y by del t and w for del z by del t, then you will get u, v and w are always equal to 0. That is, the velocity field would have to be 0 everywhere. This is obviously not the case. So this, from this we can understand that these points are fixed. The x, y and z do not vary with respect to t, because we are finding the velocity field, the derivative of the position vector at a given point. And so taking the Eulerian approach, we do not change the point. The point is fixed, and so the point itself, the x, y and z coordinates of the point do not change with respect to time. And that is why the material derivative condition also applies to the position vector. So I hope this video helped you understand somewhat this rather interesting problem. Thank you for listening.